keep it to like an hour and something.
Yeah, we'll just see where it goes. As we said, like 2 hours is more than enough time.
Okay, and we are on. Hey guys, welcome to the show today. This is Mike, and with me I have Mr. Earth Guy. Some of you guys probably know him from TikTok. He does geology videos, science videos, and he's here today to talk about things from his experience in geology as well as amazing things we want to talk about and share with you guys. Um, so yeah, welcome aboard, man. How you doing?
I'm doing well. Thanks for the invite. I suppose one of the ways to start is me to introduce myself and just to, I, as you mentioned, I do have a following on TikTok, but by all means, it's a modest following. So for those that don't know me, I go by the name as Mr. Earth Guy. The name is obviously a reflection of what I talk about, which is always all things Earth and all things geology. I I'm a sort of double master's graduate in the UK in geology for my first master's, sort of a master's. It was almost an integrated master's. It sort of allows you to move into the PhD side of the geosciences if you wish. And so at my first uni, I was like, I like where I am, but I don't know if I know where I want to go yet. And obviously, going into a PhD is quite a big task, right? It's 3 or 4 years of your life, and if you're not too sure where you want to go, you sort of need a bit of time. And during that first 4 years, I was very much intrigued by the subsurface. So if you see any of my videos on TikTok, obviously a lot of the stuff is of the earth in general, but I tend to focus quite a lot on the subsurface of geology and all the things, all the hidden things that we don't get to see. And mind you, geology is the study of that, but it was that interest for me that drove me to do a second master's in petroleum geosciences, because that is where you're studying the lower 5 kilometers of the crust to try and obviously find hydrocarbons. But I also knew that I need to work in the world and earn money. So, when it comes to geology, one of the more lucrative careers, let's say, is in the energy industry. So I wanted to make sure that I was entering the world with all the knowledge and geoscience knowledge that I could have, but at the same time think a bit more, rationally in terms of, okay, where do I want to go as a career? But yeah, that was great. And then I did my degree in Aberdeen, which is sort of like the energy hub of Europe. It's where all of the vessels are for oil and gas exploration in the North Sea. And after that, I sort of was offered a PhD, but I was like, no, I want to enter the world. I want to enter the world of careers, and get a job. And I enjoy geoscience, but I really wanted to see where my degree would take me. And then as a consequence, over the last couple of years, I've sort of gone back into the technical side of TikTok, right? Because we all know once you leave university, there are many things you don't take with you. And that's with most skills, like with maths, right? Like algebra. No one uses algebra in life, right? But you still learn it in school, you learn it in college, or what have you. So I felt myself sort of losing touch with my technical side a bit, which is why I started a TikTok channel, because then it gave me a reason to go back into academia, go back into the scientific journals, and start finding really interesting things that not only do I find interesting, but people hopefully in the world will find interesting, because we don't necessarily communicate science the best way in the world. We have, the BBC make great documentaries around nature, not much around geology, but nature. And nowadays you've seen Amazon and Netflix, and they're all sort of doing their bit to, universe shows with Barack Obama talking about the universe. Great. But there's not a lot going on with the subsurface, which is a really important part of our existence. So that's sort of, I guess, a bit of my background and sort of why I started. And I think I started just before COVID, actually, because naturally we were all housebound, and it was a perfect time for me to just make content and start pushing it out.
Yeah, awesome, man. That's kind of how I started too, and on TikTok. Yeah, so science and geology is exciting for me as well. That's why I went into it as well. I just love
Yeah.
learning about nature, earth around it. So it's a perfect segue for our next topic, which is exciting geology news. Have you heard of anything exciting? Have you seen anything amazing that just makes you go, "Wow, this is amazing" in recent news?
Yeah, so I think one of the things that I made a video on it recently. I make so many videos, I probably couldn't tell you which week it was that I posted it, but I think it was definitely 2023 that I made the video. I know that much. And I think one of the crazy things that we often discuss in the world and nature around us is the idea of where Earth came from, and where did the moon come from, and what caused. We always go back in scale in time, and we think about all those really big existential questions. And obviously, there's this discussion in the scientific forum, if you will, of the protoplanet Theia, right? It's apparently the body, the massive body in space that collided with what Earth was, helping create the moon as a byproduct of that collision. And while we do know the rheology of the moon, and we've taken samples back, we made comparisons, so we can sort of see some comparisons between Earth's geology and the moon's geology. We've somewhat lacked any major physical evidence of it really happening until we started to image the interiors of our Earth. Now, we use seismic imagery, which is where we use seismic waves, which act like X-rays or ultrasounds when you're having a baby. Same principle. Waves will go through the Earth and they will reflect and refract off different layers depending on the density changes. So one of the things that we started to see was, while we were doing these seismic imaging experiments and researches, we started to find these really unusual things in the mantle. And I say things because we have a very technical name that we call them in the geology world. We call them blobs. Yeah, I know. We couldn't have gone any more basic than that, but we call them the blobs. Yeah, the blobs. And there are two main blobs. I'm going to laugh when I say these, but the blobs. We have one under the Pacific Ocean area, and we have another one underneath the African continent. And these blobs are huge. I mean, they are massive, and we call them ultra low velocity shear zones. And the reason why we call them those is because when these seismic waves go through these blobs, they actually slow down, which is why we actually can image them, because when they pass through a change in density, a change in medium, they reflect off, and we're like, hey, we can see something beneath here, which means that if the density is different, it means there's a different density gradient, potentially a temperature gradient. Something down there is causing these blobs to be different to the surrounding mantle. And these things are massive, so big, in fact, that there's recent theories to suggest that Africa as a whole, as a continent, all of its unique geology, and it's very unique if we compare Africa to many of the other continents around the world. One of the reasons why that may be is because the blob underneath Africa is actually very close to the crust in comparison to the one near the Pacific. So that extra added heat and differential heat can cause different intrusions and different heat changes, which can create different lithologies and intrusions on the surface. Have you ever wondered why Africa is the place that has all the diamonds, why it has all of the rare earth elements? China too, but we have to ask these questions. Why does Africa have that? That collection there. So the blob is more than just a blob. It actually might have a physical effect on the surface of the Earth. But so one of the things, going back to, I guess, Theia, is there is a hypothesis going around that because there is such a distinction in these ultra low velocity shear zones, that they may actually be remnants of Theia itself. The idea that there is a different composition in the mantle that can't be explained just by natural convection flows or frictional pulling, where because of the heat, magma gets pulled up and down in the mantle, that it actually might be the remnants of Theia, that protoplanet that we've all sort of heard of, the elusive planet that created the moon, and that could explain what that is, why it's there. But again, we haven't necessarily developed the technologies yet to physically drill deep enough into the mantle due to the changes in temperatures, right? I mean, the geothermal gradient across the world is like 25 degrees per kilometer. So if the crust itself on average is 50 kilometers, we're talking very, very deep, very, very high temperatures. So maybe one day we'll get there and we'll be able to sort of start drilling in. But, for now, seismic waves are definitely the only thing we can do, but we can get a good indication. But yeah, that's some exciting things to talk about, I suppose.
Awesome. Yeah, I didn't know that. So there's giant blobs in the Earth that are influencing the continental plates of the crust. That's crazy. And I know Theia, there was a recent simulation where the Theia, the planet, we know that it really smashed into the Earth, but it was previously thought that it kind of smashed into the Earth and the ejecta kind of went into space and that slowly formed into the moon. But it's actually the fact, actually, what's more accurate is the Theia smashed into the Earth and then a chunk of the Earth got spitting out into space. And now that's just a blob orbiting and what became today's moon. So that's just amazing to me.
Yeah.
Yeah. So
No, it truly is. It truly is. And I just wanted to point out, like, while the blobs are a really interesting thing to think about, but I think the idea of seismosity itself is just insane. It's the idea that we're using waves to image something that is 2,000 or 3,000 miles deep. That is just it's mind-blowing, right? The amount of energy that we and the funny thing is usually the waves. You might ask the question, well, how do we generate the seismic waves that are capable of having that much energy? I mean, if we were to do it ourselves, we would need many nukes, very huge amounts of power to create that much seismosity. But luckily for us, well, not lucky for us, depending on where the earthquakes occur, but in terms of generating enough power, we have earthquakes, the 6 Richter scale and above, which are more than capable of creating these seismic waves. So really, the research that we do, sometimes these studies take years to complete because you may not have the right earthquake in the right location at the right scale until, you never know when one's going to strike. So sometimes these studies will take 2, 3, 4, 5 years. And most of the time, they're probably just sat there waiting, hoping that there's an earthquake of a 7 or above to make enough energy to actually image the deep interiors of the planet.
yeah, that's just utterly insane. Now, when we talk about geology, we talk about science in general, especially on TikTok or on some kind of platform where you have a bunch of people expressing their opinions and having their internal biases about their religions or their philosophies. What
Yeah.
happens is people tend to understand science. They tend to misunderstand what science means, the fact that it's not just a fact generator. What it is actually just a method. It's a method that attempts to get to the truth. And so in science, a lot of people don't understand that, well, why are there fossils on mountaintops? How can that be if there's no Noah's flood? Or how can the Grand Canyon form if there's
Yeah.
no God, no flood happen? So people need to understand that there's methodology. Also dating. People misunderstand dating. Oh, well, carbon dating's inaccurate. They don't realize that there's several different radiometric dating methods that we use to cross-reference each other. So take it back to Geology 101 for us again. How
Sure.
do we know the age? How do we know the ages of things? How do we take a look at the geological strata? How do we do fossils? How do we understand these things?
Sure. So I think one of the best places to start if we're doing a Geology 101 is the concept of uniformitarianism. Uniformitarianism is a very long word. I don't know who coined it, but it exists. And that is essentially what we see in the present is key to the past. So geology is very predictable. Like, we know how earthquakes that, occur today would have occurred the exact same way 1,000,000 years ago, 200 million years ago. The idea that, rivers deposit sediments in a certain way. If it's a meandering river, they will deposit on their banks as they go around a bend. It's a very, basic ideology, but it's an important thing to take note because we all know that rocks, at least sedimentary rocks, they form in layers, which means they normally have to form in some sort of fluid, but that fluid can be water and it can be air. So in a desert, for example, you'll have the Aeolian dunes, and they will call like Barak dunes, where they'll form really nice cross-bedding in cliffs, where you see these sandstones making all sorts of cool patterns. That's essentially, you can say that was a desert at one point. So the idea of that uniform deposition of sediment is an important one, because once we all agree and accept that processes that happen now happened prior, we can go to the first type of dating technique, which is relative dating. So relative dating is not absolute, hence why it's called relative, but it's a simple way of us being able to identify a particular lithology. So whether it's a certain type of limestone or a certain type of sandstone, siltstone, mudstone, whatever it may be, we can use geochemical analysis, so we can actually determine its composition. You know, how much feldspar is there, how much biotite, how much mica, all these minerals that exist, and we can say, okay, well, those rocks and those rocks are exactly the same because we can chemically say that they're the same, but they're in different locations and they're different thicknesses. And why does that sediment have more stuff on top of it compared to the other sediment? So the idea there is it's called relative dating, where we mix and match based off the properties of the rocks. And by logic, because we know how oceans, lakes, seas, rivers deposit, the older stuff will be at the bottom, right? That's a basic, obvious thing to say. I mean, as long as there's been no external factors like plate tectonics or an uplift or subsidence, by logic, you would say that, well, uniformly, that's how they're deposited. So that is how old. Youngest at the top, oldest at the bottom. Now, that's how we make a lot of our chronostratigraphic charts. So all of the colorful. We have that colorful scale, the chronostratigraphic scale, which we use, which has the Jurassic, Cretaceous, and all of the eons and epochs on them. That is usually done with some relation between absolute dating and relative dating, where we use the absolute dating to get the exact time, plus or minus 4 or 5%, depending on the type of dating, how much sample size you're working with. We would use that to sort of adjust how thick the band is of the Cretaceous. So we'll use absolute dating to try and figure out how old a certain rock or the range of a certain rock is. But we use the relative dating to say, okay, well, anything above the Cretaceous has to be called something else. We can't call it the Cretaceous because we have to put a boundary somewhere, a mark somewhere. So that's essentially the two types of dating we have. We have relative, which is more visual, and then we have absolute dating, which is where you brought up isotopes, radiometric dating, where we need ways to physically quantify how much or how old a rock is. And one of the main ways we do that is by using radiometric dating techniques. Now, most rocks, if not all rocks on Earth, to some degree, have some trace of radio activity with them, usually very small trace elements of uranium. But there are other elements that you can use as well, which aren't stable on the Earth's surface. And one of the ways that we do absolute dating is we look at the half-life. So we all know, for example, that atoms are made of protons, neutrons, and electrons, and different elements have a certain number of protons in relation to the electrons and their neutrons. And that is the same in rocks. So there'll be certain amounts of lead or uranium or strontium or aragonite. All of these will have their own ratio of protons, neutrons, and electrons. And what is different is some isotopes are more radioactive or unstable than others. So as they decay into other elements, they will release radioactive particles, which is why we have all of the problems around Chernobyl as a great example. Radioactivity is harmful. But with absolute dating, one of the cool things is different isotopes have what we call the half-life. So this is the amount of time it takes for one element, the parent element, to decay into the daughter element over a certain period of time. And because we have this constant half-life exist across all the isotopes, we can sort of use that half-life constant to determine age based off ratio. Now, I've used a lot of words around there, so I'm going to sort of pull it back a bit to try and make it, if you can visualize this. There'll be rock A, which has 100% uranium in it. Now, obviously, you don't want to be near that rock because, if it's unstable, you don't want to be near that. But let's just suppose that, we have a rock of 100% uranium. Now, uranium has a half-life of 4.46 billion years, right? So that means that if you have 10 grams of uranium, it would take 4.46 billion years for half of that to decay into lead, because that is the daughter element. So we know that there's a relationship between ratio of how much versus time, which is what we do in geology. So if we have a particular rock that is, you know, a billion years old, we can say it's a billion years old because we can see the ratio of uranium into lead, and as a constant. So, you know, as long as the rock itself hasn't remelted, because once you remelt it, all of the atoms get excited again and they can exist, and they're not unstable anymore. As long as the rock is set, so, you know, look at the basalts on the ocean floor, they just keep going until they get to the continent's edges of Africa and South America. As long as there's no external pressure, we can pick up a basalt and measure the ratio of uranium to lead, which can then say, okay, well, because we have more uranium than we do have lead, we know that it's quite a young rock, because we know the half-life of uranium is 4.46 billion years. And then that's one of the ways that we can do that dating technique. And addressing your TikTok comment in terms of people, you know, sometimes there's a misunderstanding of how it works, and the fact science does acknowledge that there are error margins with this dating technique, but those error margins aren't 95% or 98%. They're the opposite. They're between 1, 2, 3, or 4, 5%, depending on how much sample size you have. Because normally you would test it a few times. You won't just do the first test. You would do a few tests and try and narrow down that error range, you know, to take it from, you know, let's just say a random date of the range is from 205 to 195 million years ago. So we know there's a 10 million difference, but realistically, when we're talking about something 200 million years ago, a difference of a couple of million years doesn't really change the fact that we know at a minimum it's 195 million years old. So that's sort of the basics of how we do dating in geology. Well, the two types at least.
Great, perfect. Yeah. Remember, like, the way an atom destabilizes is a physical constant of, like, reality. It's just how atoms work, right? So that's why
exactly.
That's why. Yeah. So that's amazing. Yeah. So let's move into debunking some myths.
Here we go.
Part. So common myths: the Grand Canyon coming from a flood, the parting of the Red Sea, and you know, Noah's Ark. In general, just Noah's Ark. You know, let's debunk these myths.
Yeah, let's talk about it. I mean, should we start with the Grand Canyon, considering that was your?
Sure, where you want to start?
Yeah, sure. So I can see why people will look at a particular geological feature, or in this particular case, an entire park, you know, and notice how it almost looks like water going through, you know, if you've ever been to the beach and you sort of build a sandcastle, or you get a bucket of seawater, then you put it on the sand and you sort of see it start to very quickly carve out little rivers and stuff to make its way back to the sea. And they sort of use that logic and say, hey, well, the Grand Canyon sort of looks like a large beach where clearly a large volume of water came very quickly and it just decided to erode everything and expose, you know, literally billions of years worth of rock, because the Grand Canyon basement rock is upwards of, you know, over 1.5 billion years old. It's very, very old rock. And because there's such a lovely vertical column of young rock from about 6 million years, and then obviously we have the quaternary, tertiary deposits above that, it's easy for people to say, hey, you know what, this looks like something big happened very quickly. But that's not necessarily the case, because, and I'm going to put my hand up here and say that there is still consensus within there's still debate within the scientific community in terms of exactly what the Colorado River did in terms of its ability to erode through the rocks and when it did it. Because we know that the Colorado River, obviously in its present day, is very actively going through the Grand Canyon. I mean, all the lovely the wallpapers you see on your computer and pictures, there's all this lovely river going through the Grand Canyon. But the story sort of falls between, believe it or not, the 70 million year mark and the 6 million year mark. That's how much of a discrepancy there is in terms of whether it was continental uplift or it was more dominant by the river which caused most of the erosion that we see today. And in reality, it's a bit of both, right? So we call it the Colorado Plateau. So that is the big expanse of where essentially Grand Canyon is, as well as places like Monument Valley. You know, that we have all of those buttes with, you know, the wild, wild west, and you have all of the horses going through and those really tall structures that look like they were tree trunks, as they get called on TikTok. And so essentially what happened is, and I'm going to keep it sort of in layman's terms, is that there were a series of episodes of lakes and large bodies of water, essentially something like the Great Salt Flats and the lakes that, you know, the Great Lakes that exist in America, you know, huge lakes, but not necessarily very deep, right? So there's no geological evidence that shows that there are any deposits which infer deep sedimentation. And deep sedimentation is usually it normally has characteristics of, you know, lots of siltstones, mudstones. You know, if it's a big lake and there's no tides and that's very shallow and flat, you would expect to see certain types of lithologies deposited there. But we don't see any deposits that imply that there was a large body of water, which already gets rid of the flood idea, because that means that, you know, in order for us to see evidence for a flood, we have to see evidence for large bodies of water, or conversely, we need to see evidence of very chaotic deposits, right? Because if a flash flood comes through, we would expect to see some like turbidite deposits. Now, turbidite deposits are where you have a sequence of layers where the first layers are really heavy, because as a flash flood comes, it will slowly start to slow down. Most of the energy of a flash flood is right at the start. It will come straight through, and then once it's come through, all of the water behind will be a bit less intense, which means that slowly, as the flash flood happens, bigger and bigger sediments will come out of solution. So you'll start to get the sort of fining upward effect. We don't see any of that happening. So we don't see the chaotic deposits, and we don't see the deep water deposits, which imply that whatever happened was a very gradual but not intense thing. Now, geologically speaking, something then had to happen. Like, how do we get 1 billion years worth of geology all of a sudden visible in the cliffs? It's a huge amount of time. We don't see it in many other places. And that's where we have the tectonic uplift of the Colorado Plateau. So the reason why we have mesas, which are those tabletop mountains, very flat mesas and buttes that exist, and the Grand Canyon, is because around 70-ish, between 70 and 70 million years ago, the Colorado Plateau, which is a large expanse of land, literally tectonically uplifted. So any waters, any rivers that existed would have had to obviously carve through those rocks, because gravity works for everybody. It's not just the rivers aren't going to stop flowing. The rivers are just going to have more of a harder time actually going, which means there's going to get a lot more erosion, which is why we see really steep gorges. Because if it wasn't as intense and the tectonic uplift wasn't high enough, we wouldn't have had the really steep gorges that we see. They would have been a lot flatter, like in some of the valleys we see in Africa, for example, in those rift systems. So in essence, there's no evidence that we've ever seen that implies there was a flood on, be it fluff, ideologies, where, like, you know, the flood has to come from somewhere, but nothing on the biblical side either, which implies that, you know, there was a great expanse of water which suddenly came out of nowhere and just happened to fall around the Grand Canyon, and, you know, nowhere else. It didn't happen anywhere else, just there. So I think there's a lot of evidence that goes against why it doesn't happen. And that brings us back to, I think, the earlier discussion in terms of science. And the fact is, science is falsifiable. If we find something that goes against what the evidence shows, or if we find evidence that goes against the prevailing theory, we would accept it because the evidence is true, which means science can be falsified. So to say, and just to start off by saying, oh, well, it looks like there's a flood, therefore it is a flood, that doesn't quite work, because the hypothesis is great hypothesis. Now let's go and find the evidence for it. But unfortunately, the lack of deep water deposits and the lack of any chaotic deposits imply that there was nothing rapid like that. And also there were no big bodies of water which were just coming through and, you know, causing havoc.
Yes, it was just this slow carving away, eroding away of the Grand Canyon itself. That's how it was formed.
Yeah, and
Oh,
well, slow but fast at the same time, because if the equation never had the uplift of the tectonic plateau, then it would have been a really gradual thing. But it was quickened not because of more water or a change in river direction. It was quickened because the actual plateau, the tectonic shelf, lifted up, meaning it was further away from sea level, which means water has to work harder to erode its way down back to the ocean, which eventually is in the Gulf of Mexico, or at the other side as well, by off the west coast.
yeah. So back at the time, I believe that the Western U.S. wasn't a lot like mostly. Was it mostly water? Was there like, or was it just?
It's fluctuated. It's to say that there were times where there was evidence that there were large player lakes around when the Grand Canyons. I mentioned before that there was the basement rock of the Grand Canyon is upwards of 1.5 billion years old. All of that stuff is what we call, I think, the Vulcan or the Volcanic. It's one of the two. So correct me if I'm wrong, internet. But it's one of the volcanics. It is literally all solid base rocks. That obviously means that there was quite a tectonic regime, because volcanism occurs when plates collide with each other. So back then it was just really extreme. But then we do have evidence of layers of limestones, for example. Now, limestones happen in shallow seas, right? Like the coral reefs offshore Australia. You're not going to get limestones in any other way. They're not going to grow in the Indian Ocean the same way they do in the offshore Australia. So, and then we have evidence for player lakes, so like salt lakes. So you can see that the climate has changed rapidly over the history of the Grand Canyon. So at some point, yes, sure, there would have been a sea around that area, potentially a few deep water sediments, but none that are to the extent that would have required a flood. Yeah, because yeah.
The point is that it happened over a long amount of time. There was different variations in the speed and perhaps intensity, but the point is a lot of time, because there's different layers of the Grand Canyon, right? And that's why it took a lot of time. Okay.
Exactly.
Yeah. So let's see the next one here. Parting of the seas. Now, in the story, whatever the Bible says that the Red Sea was split, and people say, "Oh, well, we found chariots in the Red Sea, therefore it's evidence of splitting."
Yeah.
Tell us what you think.
Tell us what I think. So this is a really good question, because I remember when I was doing my first degree, and we had one of my professors. We actually had a class, not necessarily on the Red Sea and the parting of the Red Sea, but he was intrigued around whether there was any geological evidence to suggest that it could have occurred. And it was an interesting conversation, because we do see evidence in the geological record. Now, if you remember our uniformitarianism, such a long word. I'm going to call it uniform from now on. In the uniform topic, that things in the present imply the past, because the Earth has a series of processes that just follow natural laws of how things function. And one of the interesting things is that we do, for example, know that if there is tectonic activity in a certain area, it can trigger a tsunami. And what happens in a tsunami? It will pull the water out because of the difference in changes of movement of the Earth's crust. And there is evidence in the past in the Mediterranean, for example, which shows that during some tectonic earthquakes and events, water moved away from coastlines, for example. So it's not too far out the question to say, hey, was it possible that the story of the parting of the Red Sea might have been less of a godly encounter, but more an observation of something that happened in nature, and people wanted to like mythify it and put a story around, oh God, the waters have moved. It must be some higher power that's caused that. Now that's one idea. So the idea that tectonic activity or myth has come from the movement of water, from tsunamis, or changes in water motion based off tectonics, or and we know the Mediterranean's a very active area. Vesuvius is there, Mount Etna's there. There are many tectonic things happening in the Mediterranean. And while I know that's not near the Red Sea, There's question on the the translation of the Hebrew term, whether it's the Red Sea or the Sea of Reeds, which is actually a bit further up near Lake Tallinn, as it's called, near the Nile Delta. And so yeah, I've got a few takes on this. Firstly, let's talk about the physical realm of the world, right? So the Red Sea is a deep body of water, a very deep body of water. It's called the Red Sea for a reason. It is deep, and it's very, very wide. And in order for the Red Sea to have parted the way that they've said, and I don't know the from the biblical context, the exact direction that they came from, but from what I do remember is they were going from an east southeast to a northwest north, so they were going across the Red Sea, which means the Red Sea would have had to part north to south. Not even the smallest body of water, which is between the Arabian Peninsula and between Egypt. Not that way. It would have had to go the other way, which means they would have had to part the sea against its long axis of the sea, which I can't even imagine how that would even work. It's weird. It's a weird topic for me, but I did read some research, so this is where science can come into it. There was a researcher, I think his name was Crew, something Dr. Crew, and he was doing some modeling simulations on whether it's possible that what happened on the day that Moses and the parting of the Red Sea occurred was could wind have caused what they saw. So and go with me on this one. So he did some experiments and it's called wind set down. It's where if winds achieve a certain speed, I think above 60 miles per hour, the pressure of the surface wind on water can actually move entire bodies of waters out of estuaries. Now, what is the nearest estuary to the Red Sea? Well, the Nile Delta is a very good candidate. And there is evidence in the 1800s and in the 1700s of colonels that had gone there for trade and, typical colonization things which happened back in those days. They actually saw the Nile Delta dry up as a consequence of high winds that were coming in from a east to west direction. So we can conclusively say that in the record we can see that if wind is high enough, it can move water away from the estuary for nearly 3 or 4 hours, which is more than enough time for people to cross it if they wanted to cross it. So while we can talk about the geology, we could talk about how physically how possible is it. We know that science could move a body of water, but the difference here is it would have had to be near the estuary of the Nile Delta, which still technically falls in line with the story of where the Israelites were being, they're coming from and where they were going. And, hopefully it was just, or most probably it was just a translation issue of it not being the Red Sea and it being the Sea of Reeds, which is further up. And yeah, but it's one of those where at least with the flood stories, I think they have a stronger argument because floods do happen, and we've seen huge floods. Last year, Pakistan was flooded. 1/3 of the country was underwater, which is a huge amount of water. So we know floods can happen. So the idea of floods is a bit more acceptable to me as a geologist, whereas the idea of the sea just being parted, I mean, that is one of those things where you really have to see it to believe it because it's never happened before, right? So yeah, I guess that's my take on it. I don't know what your take is on it.
No, for sure. I completely agree with you 100%. Yeah. And that's amazing that wind can do that. And it's most likely, in my opinion, just another myth that was generated by people's misunderstanding of nature. That's all I think it is. Now,
which is understandable. Gonna point that out.
Okay, for sure. Yeah, but the point is, yeah. Anyway, I want to touch on Noah's Ark a little bit. And then after that, we'll go into the next topic, which is awesome. But yeah, Noah's Ark, the idea that there's a global flood, it's under my understanding that the amount of water on the Earth is, number one, small compared to the size of the Earth, but more importantly, there's not enough water to cover the entire Earth, especially not at the tops of mountains. So, is it possible that there was enough water to do this? Is it even possible geologically?
No. So one of the
Okay.
things that we can do is have a thought experiment, right? So we know the world at one point never had ice caps, right? Dinosaurs, for example, they didn't know what ice was. It was too warm back then. You know, the ice age, they weren't in an ice age, which means that water had to be somewhere, right? So if the water's not on the poles, it's somewhere in the system, right? So therefore, you could say, okay, well, you know, if all the ice was gone and all the water was melted, and you know, therefore all of the land must have been flooded to a degree. It had to be somewhere. You know, if all that water's disappeared, the trillions of tons of water that is locked up in the ice in Antarctica and the Arctic. So and even then we knew of places that were full of land. It was all land. You know, we have all the evidence that implies that there was land masses still above the water. And so that's number one. That means that even with all the ice melted, that still wouldn't get rid of all land masses from the earth, because we physically have land animals that couldn't swim, and the fact that they were alive implies that the waters never went high enough, even if we melted all the ice. Right. So that answers your, is there enough water in the world to actually cause a flood like that? The answer is no. Secondly, all we have to do is talk about the tallest mountain in the world, right? Nearly 8 miles tall, right? That's a, you know, eight. Sorry, yeah, it is, isn't it? Isn't it? Is it 8? Yes, 8,000 meters. So 8 kilometers, 8.6 kilometers tall. All of the world would have had to be covered in nearly 9 kilometers worth of water if it actually covered everywhere and got rid of everything. Now, that is just a very nonsensical thing to think about. We're talking about bodies of water taller than anything we've could ever comprehend, and the whole world was covered with it. Maybe back in the day, and when I mean back in the day, I'm talking about when land masses were being formed, where there is hypothesis that we were a water world in I'm talking billions of years ago, when land masses were still developing and volcanicity was creating land masses from you know, submarine vents and undersea volcanoes. Okay, yeah, fine. Technically, that's when the flood happened, but there was no life. There was no life back then for that flood to affect. So, but since then, no, and you have the people that say, oh, well, there are fossils on mountains, and, you know, how do you think they got there? It's like, well, you know, if you learned about plate tectonics and how orogenesis or mountain building forms, you would know that just because something is somewhere doesn't mean it naturally was in, we call it in situ, which means that it was deposited and stayed where it was deposited. We know that the Himalayan range was created off the backs of the Indian plate pushing upwards and colliding with Eurasian plate, causing the Himalayan range. And we also know that that area of land wasn't always a mountain. It was near sea level. It did have plants and vegetation and animals and fish underwater, shoreline fish. We know that those rocks there were under the water, not just because of the fossils, but the types of rocks they are. You're not, if they're sedimentary in nature and they've been metamorphosed, so that is the idea of pressure and temperature altering a sedimentary rock. And it can happen to igneous rocks as well. But you know, when heat and pressure is applied to a sedimentary rock, it will change its form. Like limestone will turn to marble. So marble doesn't form naturally by deposition. It has to be heated and compressed and pressurized. And you know, so technically, because all limestone that exists was once part of life. Corals, calcite, calcium carbonate, most of this stuff which is biologically, organically created. And therefore, you know, your kitchen countertops are made technically of old dead things from a gazillion years ago, you know? So does that mean that they naturally formed in the kitchen? No, it doesn't. Things have happened to that limestone, which means that it exists where it does. So while I appreciate the observation of seeing and finding things, it's the lack of understanding. It's the lack of understanding that when something exists out of situ, which means not where it was originally deposited, it means that something happened along the way. In this particular case, it was the fossils on the seafloor being pushed up to the top, and now they form part of the Himalayan range, which is, you know, thousands of meters tall, and that itself doesn't constitute evidence of there being a flood, because if there was a flood, why don't we see evidence on every mountain peak of there being corals? Every mountain peak would have corals on there if they all went to a certain height, because that's just how corals form. They love shallow seas. They love warm waters. So we'd have corals on every single mountaintop, but we don't see that because guess what? They weren't underwater.
Yeah, actually, fun fact: the Floridian Peninsula is the bedrock that is the foundation of our entire state of Florida is literally limestone. Literally, it's shells and coral reefs that have died in the past and pretty much deposited there. So, and there's actually springs in Florida that I've gone to, and you can actually see it's right near the aquifer where the water seeps up from underground. You can
Nice.
see the limestone. It's really beautiful.
No.
Anyway, yeah. So
it is.
we have about 20 minutes left.
Yeah, sure.
I want to talk about human evolution. So a lot of people don't understand why humans are human. Like, what makes us human? And I always show people that in Africa, 6 million years ago, there was climatic changes that happened, and they kind of pressured our species to change. So can you delve into those kinds of climatic changes and perhaps geological forces that went into making humans evolve?
Yeah. So what I'll do is I'll talk around one of the ways that we understand evolution, at least from a geomorphological point of view. So in order for evolution to occur, obviously we have the natural mutation, right? The natural rate of mutation. That is a metabolic rate of how frequently things mutate through offspring, and it continues to go through. And whilst those mutations exist independently as to whether it's good for the species or not, it's the environment through natural selection that determines whether those mutations are good mutations, right? Now, therefore, the environment obviously plays a very key role in the migratory patterns of animals, for example, like ice ages and the influence of atmospheric and oceanic conditions. They all influence all forms of life. So whilst this is about human evolution, it's important to understand that is the reason why nearly all things evolve. That things don't evolve just for the sake and for the fun of it, right? Evolution is one of those things where it will happen independently, and it's the environment that will help determine as to whether those new mutations are naturally selected. And you're quite right. So the idea that geology, or let's just say the environment, the effect that has on human evolution is profound, because we do know, we have the famous out of Africa theory, which sort of indicates that all the Homo sapiens they sort of migrated outwards, and we do see evidence now of interbreeding, which is a really fascinating topic. The idea, I mean, last year's or 2021's Nobel Prize was on the sequencing of the Neanderthal genome, which now allows us to see that, hey, a lot of people in Asia and Europe have between 2 and 3% Neanderthal DNA in our genome, which is mind-boggling. And it goes one step further, is some of the Aboriginal Australians have 4 and 6% Denisovan DNA in their genome. So obviously we're finding out a lot more that evolution isn't just this slice, isolated, you're one species, or you're one subspecies. We're actually learning more and more that we're more closely connected than we previously thought. And when it comes to, as you rightly mentioned, there is evidence in the record that shows that there were, at least geologically speaking, in the last between 5 or 6 million years, is climate change isn't just a now phenomenon. Climate change has been a thing that humans have always had to struggle with. We see evidence of mini ice ages that they had to deal with. There's a great there's a hypothesis currently as to how certain species of human got to mainland America, right? Could it have been through the Bering Strait, which is that connection between Alaska and Asia? Because there's no way, for example, that humans would have crossed the Atlantic Ocean. I mean, they didn't have boats. I mean, what were they gonna, what were they gonna get across on? But one of the places they could have gone across, just like slowly swimming their way across. But one of the things we do know is through simulations and through modeled results, we can show that the Bering Straits during the peaks and sort of the mid peaks of the ice age, there would have been land bridges, ice bridges, essentially frozen parts of land and permafrost in that area, which would have allowed things to migrate over. And that's how some of the more native animals on America could have independently evolved. There are certain bison exist across the world, but why does certain bison only live in America? That doesn't exist. What characteristically changes them from the Asian bison to the North American bison? Well, firstly, how did they both independently get there? Well, they could have gone across the straits, right? So the main push, and one of the geological factors for people moving northwards is you have. I mean, we see it today, and the reason why I'm trying to answer this question in a correct way is because with geology, we've got to be careful where there's no for example, let's talk about volcanics, right? When a volcano goes off, and it's a huge volcano, let's think like Pinatubo or something as big as that sort of caused the planet temperature to decrease by a couple of degrees, right? And this is Pinatubo's it's gone off many times in the past, and through the geological record we can see that there was a downturn in limestones being created, which means the temperature decreased. So there are things like that which we can, proxies that we can see. And when it comes to human evolution, one of the things that definitely would have made a factor is things like temperature, right? Now, this, I guess, comes out of the geology realm, and we're now more into climate sciences. But I have no doubt in my mind that part of the reason why humans ventured out of Africa was it would have been both climate dominated. So the idea of maybe weather was cooling down south and they had to move north towards the equatorial regions. But also changes in temperature also mean changes in food and the availability of food, which means that we as a species very successfully are great marathon runners. We're very good. We're not the best sprinters, but we are very good marathon runners with lots of stamina. And our migration capacity is, whales can migrate, thousands of miles every year to go and give birth, but we just migrate better and we acclimatize and adapt to all environments a lot better. Right? We don't go to one place for a particular purpose. We will go to a place and use everything that we can because we're very agile and we're able to do that. That's one of the reasons why we probably took over from Neanderthals. We learned to integrate. We learned to do what they did. We learned to live where they lived. We inbred with them, and we literally bred them out of existence because we were just that good at what we did. And same goes for the other species and potentially the Denisovans. But I think it's a hard topic to try and say why did certain things happen. So going back to your point, I would say yes, climate was probably a dominant factor, a very dominant factor, and probably things like changes in their food and their we talk about the cognitive revolution and creating civilizations and societies, and obviously these things we're fast forwarding quite here from millions of years ago to hundreds of thousands of years ago, but I think it all adds to why we keep moving as a species from one place to the next place.
Yeah, and specifically, I believe that there was change in Middle Africa, Central Africa, where I guess trees became less or sparse, and it forced a lot of the tree-dwelling apes to leave the trees for the first time and try to. They didn't start walking. Obviously, they were kind of forced out of the trees. They had to venture further and further out of the trees and onto more land. And over time, the ones who were better adapted to walking or using their 2 feet more, or the ones with the mutations that is that accurate?
Yes. Yeah, exactly. So it's you said it quite right. It's like you have to. It's quite weird because you have to sort of formulate a story in your mind as to what could cause something, right? So one of the things could have been things like that. So you have as temperatures changed, as environments changed, obviously we have some of the biggest, like the Sahara Desert is one of the biggest deserts in the world, and desertification is a thing where deserts will just spread. So people don't realize that deserts actually move. Like they exist in one place, but they will grow and shrink depending on the wind and the temperatures and the availability of sediment. And desertification is a killer. Currently, China is building what they called the Great Green Wall of China, basically planting forests around the Gobi Desert area to stop it infringing on their country and taking over towns. It's a really big thing. So
Wow.
the idea that temperatures change and temperatures cause changes in like forests and how big they can be could be a real factor as to what caused apes and our ancestors to have to move, and only those that had the ability to move quickly and faster and essentially have the ability to kind of walk on two legs if they had to, they're the only ones that survived, because the other ones died because they just couldn't keep up. That's natural selection at work. It's brutal, but it's true. The same goes for when Chernobyl went off. Many of the animals died, but guess what? It is now being reflourished with brand new species and new adaptive species, because those that survived the radiation manages to hold that through natural selection. And that would have happened with us as well. The idea of by being bipedal would have been I like to say like an exaptation. So exaptations aren't quite adaptations. It's where one thing can sort of have many uses. Like, for example, your hands, as an example, how you move them. Like, I highly, your thumbs weren't made for holding iPhones, were they? That's an exaptation. We've learned to use our hands to do many different types of things, right? The same with wings. Wings weren't always used for flying, right? Flying was an exaptation of wing development, and these are things that we can look at which help us. And yeah, so I think it's a really interesting topic, though. I mean, I'm keen to get your input on it, because I know when we do like TikTok lives and stuff, like you do have a really good, like, vested interest in evolution, and you like talking about things. But what are your thoughts on so if you fast forward from the why, from a geological sense, did humans move and migrate? What's your opinion on the evolutionary journey of humans, let's say, since we developed into society? Like, how do you think that went about from your personal perspective? Like, how did society develop? Like, how did we go from nomadic herders to how civilizations are?
There's a billion factors, like you said. There's a billion different factors, but I would say mostly is what made us human is language. When you live in tribes together, when you live together very tightly, you
Yeah,
tend to want to communicate with each other. And language, what language did was allow us to share knowledge with other people, and that knowledge could be passed down through generations. And after that
yeah,
happened, the fast forwarded that it was an exponential snowball effect on
sure.
advancements technology, because that allowed us to do anything we wanted to and share it with people in the future. So but language is something that I think is common, and it's humans are the only ones that have language, but many animals have precursors to language, like whales, for example.
Mm.
But the point is that language is something that evolved in us and helped us most. Fire as well, cooking our food, enabled us to get more calories per
Yeah,
meal, and we can extend the distance of that food in our travels. We can
exactly.
find any food in nature and use that for advantage. But yeah, the main thing to me is language. Also, perhaps, I hate to say it, but maybe even religion, maybe
Yeah,
cults, religion. It
I
kind
think, but
of
that adds to it, right? Because what you just said is and not to be, not, I respect everyone's beliefs, and you, if anyone follows me on TikTok, you'll see I purposely don't go into sort of debates on this, but you sort of mentioned language, and you mentioned and stories, right? The idea of language allowing us all to sort of unify and have a common way of communicating, and stories almost provide a series of awe and hope. Like, there's lots of evidence to suggest that the feeling of awe when I think it was first coined by there's a name for it, and I can't, it's on the edge of my tongue, but it was the effect where the first astronauts that went to space and they saw Earth for the first time back on themselves. There's a name like of the effect, but I can't, again, you have to Google search it. But it was the sense of awe actually has positive impacts on human cognitive development. It's not just a feeling you get, it actually makes you feel good, and it helps your brain. It helps grow the neurons in
yeah.
your brain. So the idea of storytelling, if done right, can give you that sense of awe with imagination and thought, saying like, wow, is that true? did giants really
Wow.
exist? No way, I can't. But these things actually, weirdly enough, help the brain develop in a cognitive way. So
Wow.
storytelling is a powerful method for not just hearing about cool stuff, but it actually develops the brain by having those chemicals released in your brain. So I feel like,
Amazing.
as you mentioned, language, story, religion, they all provide awe. Even if people may not be religious, but you can appreciate that a very pious and religious person, they probably experience awe every day praying to God. They probably do. Like a really pious person, when they're so
Oh yeah.
deep in their belief, and
Oh
that
yeah.
is that by itself is making their brain grow better, because they're having those experiences and those things in on their inner. So I wouldn't be surprised if the idea of language, storytelling, and religion, and
And
you know
music.
and
Music as well.
music,
That would
trance
yeah,
and music, 100%. And that sort of leads into that really cool discussion where that might explain why humans, since the dawn of agriculture, have been obsessed with worship, obsessed with mythology, obsessed with stories, obsessed with all things related to irrational or non reality,
cults too.
super. Sorry.
Cults like
Yeah,
being making.
yeah. I mean, why
Um,
do we do it? I was watching a Netflix series the other day on Waco, in America, where that the Davidians, he was a guy that claimed to be a prophet, and he had like 90 people that worshipped him, and they died with him. They died with him. He said he was the Messiah returning, and they had one of the largest shootouts with the ATF and FBI in America, in Waco, in a town called Waco in America. And the standoff was 51 days, and they were having gunfights full of armor, vehicles, tanks. And I watched it, and I was like, how in 2020, well, this wasn't 20, this was back in 1993, but how in the 21st century and the 20th century are people still able to be brainwashed
deluded.
to that extent where, like, okay, fine, you can talk as much as you want about Islam and Christianity and Judaism, like, it's one of those where it goes back millennia and the stories are very developed amongst all of society. That's one thing. But then to have some guy come up and say, hey, listen, I'm Jesus, I'm the new guy, I've come back, and you all have to come, and
It's really
he had 90 people that followed him to his death. And I'm just sat there like,
yeah,
to believe in someone so much that you literally will die for them. And then that just goes back to that we have evolved as a species to believe the stories that we've been told from authority. It's not
yeah.
brainwashing can happen and that's what it is. We've evolved that ability because stories are important, stories are powerful, because stories have helped our brain grow, literally.
Yeah, and we should have another discussion about evolution, but I want to move on to
Yeah.
the geology here. And last topic we'll talk about real quick, then we got to go about Antarctica.
Yes.
So I've heard that obviously under Antarctica, under the ice sheets, right, there's land, and
Yep.
there's evidence of fossils, there's evidence of life, and there's also evidence of rivers underneath the ice of Antarctica, and we've
Yep.
actually found several different dinosaur fossils. So, I mean, what do you think? What else could we find underneath the ice of Antarctica? Do you think?
So I say we're Americans say Antarctica, I say Antarctica. It's the same exact thing. It's just a language thing. Again, language. So sorry.
Yeah, that's my fault. But yeah, go ahead.
Oh, no, it's not. It's no one's fault. British versus American. We can have that debate another time. But yeah, so Antarctica is a really interesting continent, right? Because we obviously know it has really thick ice shelves, and for a long time we wondered what was beneath Antarctica. Like, we've done drill cores, and we've seen, we found brand new species of molecular, like, living organisms that live in the waters beneath of an Antarctica, which we've never seen before. So there's an entire biome of life that exists under the ice, and one of the interesting things is we know that land exists beneath Antarctica because we see the arêtes of mountains. Like you've probably seen a gazillion conspiracy theories on YouTube saying, you know, that Antarctica has pyramids, and it's like, come on, guy, Antarctica doesn't have pyramids. They're not pyramids. What you're looking at is arêtes. It's literally the peaks of mountains, of rocky formations that are piercing through. And in cold regions, arêtes literally form in rare occasion pyramid peaks that they literally cause because in cold environments where there's a high range of temperature difference, and it doesn't have to go above zero, it can still be below zero, but if there's enough of a pressure difference, the mixture of moisture and ice will cause fractionation in the rocks, which when rocks fracture, they fracture at angles, right? So the fact these arêtes form because of the angular erosion of glaciers, if they exist, but also because it's called freeze thaw weathering. That occurs where they create these really like angular tops, which is why in like the Alps and things like that, a lot of mountains will have tall peaks, is because ice and thawing causes that erosion, which is what causes those. And so we knew land existed beneath Antarctica. What we were surprised was to find the Ghost Mountains. So this is a mountain range which forms. I mean, I think it's like 3 or 4 kilometers beneath the ice, but it's the size of the Alps. So if any of you know the Swiss Alps, it's one of the largest mountain ranges in Europe. So these mountains, which are hidden under the ground, under the ice, are as big as the Alps, which is mind-blowing. It's a huge area.
Wow.
And one of the things that they found interesting when they started digging down into the core is they realized that the mountains were really well preserved. And you mentioned rivers, and this blew my mind. I probably should have brought this up. I probably should have brought this up at the start when you said, "Hey, have you got any cool geology stuff to talk about?" Is under the ice of Antarctica, the rivers flow uphill.
Wow, is that because the pressure different?
Yep.
Pressures are different?
Yep.
Wow.
Yep. So we mentioned before around the geothermal gradient, right? Where everywhere on Earth has like a geothermal gradient of like, so it's around 25 degrees per kilometer because the internal of the Earth is warm. So naturally, there is a temperature difference between the ice above and the rocks below. Now, while the rocks on the surface, because they're touched by ice constantly, they will obviously melt to a certain degree, and as you mentioned, make underwater rivers. But because it's got kilometers worth of ice underneath, above the mountains, the water hasn't got many places to go except upwards due to the pressure differences. So you've got the weight from above pushing whatever it can, and because the mountains actually form as a conduit to flow, because obviously the water can't go anywhere else, so it's going to go up the side of the mountains because that's where there's less pressure. The water goes up to the top and it refreezes at the top of the ice and it repeats the process. So there's almost like this like micro weather system without clouds. The ice itself is the clouds because the ice is what melts to make the water flow, but then it goes back up to the top and it refreezes again.
So when it goes to the bottom, it melts again, and then it.
Yeah. So the ice. Yeah.
It fuels the water to go upwards.
Yeah, so you almost have, imagine, so you know how normally rain starts at the top of mountains and comes down the mountain and then it goes into lakes and then evaporation goes into the cloud, goes back to the top of mountains and it rains again, right? That's the standard the water cycle. Imagine the opposite occurring in Antarctica. The water isn't going to be created at the top of the peaks because that's colder than at the bottom. All the ice at the bottom, on the bottom in the valleys of the mountain, that's the part that melts because it's actually closer to the warmth of the crust. That water goes back up the top of the mountains, refreezes, and it's like an inverse loop of the water cycle, which is, it's just crazy. It's just crazy to think that happens. The inverse of what happens on above sea level happens down there. But more importantly, that water movement also protects the mountains, because when we did coring down there, we were like, wait a minute, if we've seen how glaciers work on mountains, they erode. Like glaciers will bulldoze their way through rocks. Why aren't these mountains gone? If there's this much ice above the mountains, why isn't the ice just eroded all of the mountains away through like movement? And Turns out it's that water recycling which shields the rocks of the mountains itself. It creates a lubricant around the mountains. So even though the ice exists and the pressure exists, the water itself, which goes uphill, actually lubricates the mountains and protects the mountains from being eroded.
Wow. Okay. That's crazy.
If that
So
makes sense, which is why
water,
the mountains still exist.
the water stops the mountains from sinking.
No.
Or
It stops them. So the warmth of the imagine you have a hot knife, right? And you have a cold knife, and you put the hot knife through butter. Because the knife is hot and it melts things as it touches, it goes through the butter really nicely. So imagine the opposite occurring. You've got the ice on the top going across the warmer crust below. Because of the difference of temperature, it melts, which means that it doesn't have the same erosional capacity, because ice itself will erode a lot easier than water in terms of brute force mechanics, right? So a glacier, as an example, will carve its way through a valley. A river will be able to do that, but it will take a river a million years longer to try and do that, because water doesn't have the same erosional capacity as brute hard strength of a glacier ice wall grinding against the rock.
Okay.
So what
So
happens down below? Yeah, what happens below is because of the temperature of the continental crust in relation to the ice above it, it is consistently melting the ice and refreezing, but that process protects the actual mountain itself from being bulldozed and eroded. And yeah, so it's a whole different world, and that all of that happens because of pressure, and well, I guess ice as well, that helps. But yeah, so while we, yeah, it's just madness. It's just a mad thing to visualize, really.
Yeah, that is crazy. That's insane. And it allows us to understand more about potentially ice on like Europa or like Enceladus, for example.
Yeah.
Who knows what can
Exactly. And all of these things help in that understanding of, when it comes to studying meteorites and water and where life can and can't exist, in the hydrothermal vents of the oceans where it's 400 degrees. There are species that exist there that exist nowhere else. All of these things that we study on Earth have the ability and the potential impact on if we go to another planet. Just because life isn't existing on the surface doesn't mean it's not existing below, because we've seen here on Earth, in the most inhospitable, toxic, non-oxygenated environments, we still find microbes living and thriving and having entire ecosystems.
crazy.
So I have no doubt that I wouldn't be surprised if there are many planets or many bodies of rock, if you will, in our solar system, which have some sort of microbial, just stuff like little water bears, as you call them, that don't need anything to live off. They just exist, and they're just like floating around on rocks and stuff.
Yeah, who knows what's out there, man? But I really, anything else you want to add before we go? Anything you want to talk about?
No. I think we've covered quite a bit today, but I think we've opened up a few topics, and then maybe in a subsequent video we can go further on those, or we can, let's see what people who listen, they might want to have some, they might choose some topics that they were really interested in, and we could have a, another discussion around, a bit more in depth and technical. But yeah, I just appreciate you asking me to come on, and I really enjoyed it.
Yeah, for sure. We'll definitely have more discussions, and yeah, like you said, if you guys have any questions or you want to bring up something, a topic, let me know in the comments. Let us know, and we'll discuss it. Again, appreciate you being here, man. Everybody, go follow MrEarthGuy videos, and that's it. Thanks for being here today, man. That's awesome. Great. We had a great discussion. Thanks.
No, I agree. Yeah, and thanks everyone for listening, and yeah, look forward to the ones to come, and appreciate the invite. Haven't done one of these in a while. Last time I did one was with my professor years ago, and it beats speaking to yourself on the phone, making a story or talking about something. It's nice to have an actual conversation, which isn't a debate where everyone's like hounding at you for saying something or not. So it was quite nice. So appreciate it.
Yeah. Okay, man. Well,
awesome.
Bye, guys. Everybody, goodbye. Have a good day and enjoy the weekend. Thanks.